You know black holes, right?
Yeah.
Like, everyone has this picture in their head.
Yeah.
Like, these, like, ultimate prisons.
Yeah.
Where nothing escapes. Not even light.
Ultimate cosmic vacuum cleaners.
Yeah.
Yeah.
But it's, like, kind of a paradox when you think about it, because they're also the source of, like, the most crazy, powerful energy displays in the universe.
Absolutely.
These huge jets of particles blasting out, you know, and those
super energetic
gamma ray bursts.
Right.
You know,
gamma ray bursts.
And you sent in some really fascinating stuff. Like, you guys are on top of it.
I try to be.
Tackling this big question.
Right.
Where does the insane magnetism needed to, like, fuel these cosmic fireworks actually come from?
Where does it come from? Yeah.
Yeah.
It's a big mystery.
It's a huge mystery.
So today we are going on a deep dive.
Let's get into it.
All right.
Yeah.
So you sent over this study
from
the Flatiron Institute.
Yeah, the Flatiron Institute.
And
it's in Astrophysical Journal Letters.
Okay.
Pretty prestigious.
Yeah.
Published.
And it's from a bunch of different researchers.
Yes, it usually is.
What's really interesting is, like, they're proposing, like, this wild, kind of surprising answer.
Yeah, it is.
To this, like, really
long-standing question.
Big question.
Yeah.
It's been around for a while.
Yeah, yeah.
So
that's what we're going to unpack today.
Exactly. We're going to try to understand how black holes might actually be inheriting the magnetic fields that power these amazing events.
Yeah. So, I mean, just to kind of set the stage.
Yeah.
You know.
Yeah.
Like,
give everybody.
Black holes are born from the deaths of
catastrophic
stars. Yeah. Catastrophic collapse.
Right.
Yeah.
Supernova explosions.
Supernova.
And then they become these, like, super
incredibly
dense objects where gravity is
intense.
So intense.
Yeah.
That it warps.
Space-time.
Space-time.
Yeah.
Right. Like, it's so...
It's mind-boggling.
Mind-boggling.
It really is.
To even try to conceive of it.
I know.
But it's almost like a contradiction, right?
Yeah.
To think that something...
It's a paradox.
That's defined by its ability
to every time.
Also launch these
crazy, unbelievably powerful
energetic outflows.
Yeah, these outflows, these jets.
Right.
And the research that you sent points to these strong magnetic fields.
Strong magnetic fields are key.
They're like the key to this.
Yeah.
But the big question is,
the buzz.
Where does that magnetism come from?
Right.
Like, in the first place.
That is the question.
Yeah.
That's been bugging astrophysicists.
Yeah.
For decades.
For a long time.
It's a fundamental question.
Yeah.
Yeah.
So this study you sent is really interesting.
This is where it gets cool.
It's like, it suggests this wild idea that black holes aren't, like, creating this magnetism out of nowhere.
Yeah.
They're actually inheriting it. From the stars that died to create them.
It's like a cosmic inheritance.
Yeah, like a legacy.
A legacy.
Exactly.
It's crazy.
That is.
It's really cool.
Yeah.
So these researchers are proposing that the link is
missing link.
This thing called a proto-neutron star.
Oh.
Proto-neutron star.
This is like
a phase right after the supernova. It's this brief but crucial phase.
Like right before the final collapse into a black hole.
Right before it becomes a black hole.
And I love how...
Or Gottlieb.
The lead author.
The lead author put it.
He had a great analogy.
He said,
proto-neutron stars are the mothers of black holes.
Yeah.
In that when they collapse, a black hole is born.
It's true.
I mean, how cool is that?
It's so cool.
Yeah.
And it seems
like this mother...
This mother's
passing on a
important
trait.
Yeah.
Magnetism.
Yeah.
So in those
fleeting moments
before a proto-neutron star becomes a black hole,
right?
It can have this it
can have a swirling disk of material around it.
Yeah.
Called an accretion disk.
Like stuff swirling around it.
Yeah.
And the study suggests that
disk plays a key role.
Is key
in essentially pinning.
The
existing magnetic field lines of the proto-neutron star.
Onto
the newly forming black hole.
Yeah.
It's like, Imagine.
It's wild. Yeah. Imagine if you had like a tangled...
Yeah. A tangled ball of yarn.
And
you're trying to transfer it.
And you're trying to give it to someone.
Yeah.
That disc is like a way to hold...
The disc is like the hand that holds onto those threads.
Those magnetic threads during the transition.
During that crucial transition. Yeah.
Oh, I love that.
It's a good analogy, right?
That's such a good analogy.
Yeah.
So now...
Now there was this.
There was like this...
traditional.
Yeah, like a traditional idea.
About where this magnetism came from.
Yeah.
The thought was that as the star
collapses
and shrinks
down
to become a black hole,
down to this tiny black hole, any existing
magnetic field within the star would just get squeezed,
would just get like compressed,
amplified,
like intensified.
Like imagine compressing a spring, its force becomes stronger.
Right. That makes sense.
Yeah, it's logical.
So huge star,
massive star,
shrinks down to this tiny black hole.
Yeah.
So
with this tiny point,
everything in it,
you would think would just get
everything gets
packed in and intensified.
Yeah.
Including the magnetic fields. But this study points out a flaw.
It's like
there's a flaw in that thinking.
There's a problem, a critical flaw with that idea.
Right.
And it has to do with...
And it comes down to...
how fast the star is spinning.
How fast the star is spinning.
Right. So, strong magnetism. Within a star.
Acts like a brake.
It actually acts like a brake.
It's slowing down the rotation.
Slowing down its rotation.
Yeah.
Okay. So why is rotation...
Now, why is that important?
So important.
Why is rotation so important?
Because
rapid rotation is essential for the formation of what's called an accretion disk.
An accretion disk.
Yeah.
Which we were talking about before.
That swirling collection of gas and dust.
Stuff swirling around.
That orbits the black hole.
Yeah. And this disk is like super important.
And this disk is crucial.
Because
it's the interaction of that material with the black hole's magnetic field. That powers.
That ultimately powers.
Those jets. And gamma ray bursts.
Crazy jets.
Yeah.
And gamma ray bursts. So it's like...
So it's this kind of...
Catch-22. Gottlieb said it's...
As Gottlieb pointed out.
Mutually exclusive.
It's mutually exclusive.
If the collapsing star has...
a
super strong magnetism.
Strong magnetism that gets compressed.
Yeah.
Amplified.
It
won't be rotating.
Fast enough to form that disk.
To make that disk.
Right.
But if
the magnetism is weaker...
The magnetism is too weak.
Yeah.
And it allows...
Which allows rapid rotation.
Test rotation.
And disk formation.
On the disk to form.
It might not be strong enough to power the jets.
It might not be strong enough in the end.
Yeah.
To power...
To generate those powerful jets.
Those huge jets.
Yeah.
It's like...
So it's a real
problem.
Sticking point.
Yeah.
In understanding...
It was like a block.
Yeah.
To understanding these events.
These phenomena.
Yeah.
It was a puzzle.
So... The reasoners...
Had a realization.
Had this like... A real aha moment. Yeah. They realized that proto-neutron stars themselves.
The proto-neutron stars themselves?
Kind of like accretion disks.
Yeah. So.
Earlier simulations and theories.
Yeah.
Sometimes focused on either isolated neutron stars.
Okay.
Or fully formed black holes.
Right.
So they may have overlooked this really important intermediary stage.
Right.
And the disk
missing
that could exist
at this step
around it.
Yeah.
Yeah.
So the black hole isn't
starting with a clean slate.
From scratch.
Magnetically speaking.
Yeah.
Right.
Magnetically speaking.
It's inheriting a system.
Yeah.
The proto-neutron star.
Yeah.
And its surrounding disk.
Yeah.
That already has a magnetic field in place.
It's bringing something with it.
Yeah. It's a pretty neat solution.
Really cool.
Yeah.
So the idea...
is that as the proto-neutron star...
that
final collapse to become a black hole.
Yeah.
This pre-existing accretion disk...
Yeah.
With its...
embedded magnetic field lines.
Just
passed on.
Gets passed on.
To the baby black hole.
To the newly formed black hole.
Yeah.
Those magnetic fields.
Oh, like a hand-me-down.
Yeah. It's like a hand-me-down.
It's crazy.
From the mother neutron star.
Yeah.
Essentially get anchored in the child.
Yeah.
Black holes.
Black holes.
Freshly formed disk.
Newly formed disk.
Yeah. And you know what?
What?
They actually made an infographic.
Oh, cool.
Yeah, it's called Black Hole Magnetism Infographic.
Oh, wow.
And it visually explains this inheritance process.
Oh, that's cool.
It's really well done.
That's awesome.
Yeah,
so this isn't just like a...
This isn't just theoretical.
Theoretical concept.
Right.
Right.
They did the math.
The researchers backed this up.
They backed it up with calculations.
With calculations?
And simulations.
With simulations.
Yeah.
What did they find?
What did they find out?
About the timing of all this.
About the timing.
Because it seems like...
Yeah, because it seems like...
And then we're half bit.
This magnetic field transfer...
Quickly.
Would have to happen really quickly.
Before the field.
Before the field weakens.
Weakens or disappears.
Or disappears.
Yeah.
Yeah, that's a great point.
So
the team's calculations...
Yeah.
Showed... that generally speaking, the time it takes for this black hole disk to form and settle around the new black hole is typically shorter than the time it takes.
Than the time it would take.
For the black
hole.
To lose a significant portion of its magnetic field.
Oh, wow.
So that difference in time scales is key.
That's the key.
It's the key. That timing, as Gottlieb said, the disk enables the black hole to inherit a magnetic field from its mother. The neutron star.
That's so cool.
It is really cool.
So this discovery
is really exciting.
Really exciting.
Because not only does it provide a really good answer to this question.
It's this mystery
of where black hole magnetism comes from.
Yeah, where that magnetism
also has wider implications.
Has so many other implications for how we understand.
Other events.
Other powerful events involving jets. Across the cosmos.
Across the universe.
Yeah.
Right?
It's huge.
Huge.
So
Gottlieb
and the team
are really excited. Because it opens up new ways of thinking.
Yeah.
About jet formation.
Like
throughout the universe. As Gottlieb said.
How we think of
if we know that accretion disks imply magnetism, then in theory all you need is an early disk formation.
It's an early disk.
To power jets. So this suggests that jet formation
it might
be a more common phenomenon in various cosmic systems than we previously thought.
Yeah.
It really makes us rethink.
It changes everything.
The connections.
Like a paradigm shift.
Between different types of stars.
Yeah.
And the prevalence of these...
groundbreaking.
Energetic jets.
And Gottlieb also mentioned something...
He emphasized
really important
the collaborative nature of this research.
The research.
And the crucial role.
That it was a collaboration.
Played by the resources. At the Flatiron Institute.
The Flatiron Institute.
Center for Computational Astrophysics.
Yeah.
The CCA.
The CCA.
It wasn't just a solo.
Yeah, he made a point of saying...
moment.
That it wasn't like...
It was a concerted effort.
Just him by himself having this like...
Utilizing serious computational power.
Yeah.
Yeah.
It
was a team effort.
A team.
Absolutely.
And a lot of resources.
Absolutely.
Yeah.
And he specifically highlighted...
And he said...
The multidisciplinary expertise... within the collaboration.
That was key.
Bringing together researchers.
Yeah.
With different specializations.
Yeah.
In astrophysics.
All these different people from different
people with different backgrounds. Coming together.
And also that the ability...
Consistently run. These complex simulations. Thanks to the resources available at the CCA.
Yeah.
Was vital.
Super important.
Absolutely crucial for putting together this picture.
For putting it all together.
Of a star's final moments.
Yeah.
And the birth of a black hole.
Yeah.
Yeah.
So for our listener,
right,
some of this stuff might be new.
Yeah.
So we've been talking...
Just to clarify.
About accretion disks.
Accretion disks, yeah.
That's so...
In the simplest terms, what are they?
In simple terms, what is that?
An accretion disk is basically a cosmic whirlpool.
Okay.
It's a rotating collection of gas, plasma, dust,
and other particles. Okay.
That accumulates around a massive object.
A massive object.
Like a black hole.
Like a black hole.
Due to its gravity.
Okay.
So the material in the disk gradually spirals inward.
Okay.
Towards that central object.
Okay.
Yeah.
Makes sense.
Right. So
and we've also mentioned.
We've also talked about these
gamma ray bursts.
Gamma ray bursts.
Yeah.
So what are those?
So what are those in essence? Gamma ray bursts are like the most luminous and powerful explosions we know of in the universe.
It's crazy.
They release.
They're huge.
A tremendous amount of energy.
Yeah.
In a very short time.
Yeah.
Often just a few seconds.
Wow.
And they're frequently associated with the formation of black holes or the merging of neutron stars.
Wow.
Yeah.
It's pretty intense.
Just to give credit where it's due.
Right.
For the authors of the study.
This study that we've been talking about
we've been discussing
was a collaboration.
Yeah. It was a collaboration involving Or Gottlieb.
Oh, cool, Gottlieb.
Brian Metzger. Jared Goldberg.
Matteo Cantiello.
And Matthew Renzo.
Yeah. And they're all connected to...
the Flatiron Institute, Center for Computational Astrophysics.
CCA. Or affiliated
institutions. And their research.
Was published...
It was published in...
In the Astrophysical Journal Letters.
On
November 18th. 2024.
And you can find it.
You can find it using
the DOI number.
It's a DOI number.
10.3847-2041-8213 had 8563.
10.3847-2041-8213 8563.
And it's also worth noting that...
Their work relied heavily on...
sophisticated computer simulations.
Including
the creation of 3D visualization.
So
like really understand
its
process.
These complex processes.
Yeah.
Yeah, those detailed simulations...
It's amazing.
...are crucial.
For
unraveling... the intricate dynamics of stellar death and black hole birth.
It's really...
They allow researchers
incredible
to test these theories
in
a way
and it's stuff
that observational astronomy
couldn't do before.
Alone cannot.
Yeah.
So to bring it all together.
For
our listener. The long-standing puzzle.
Big question.
Of how black holes acquire their incredibly strong magnetism.
Gets so magnetic.
Seems to have a compelling solution.
Seems to have an answer now.
The research suggests that they inherit these magnetic fields. From their progenitor neutron stars. Through the vital intermediary of the accretion disk.
Yeah.
That forms around the protoneutron star.
Yeah.
Just before it collapses.
It's crazy.
Yeah. So, and this inheritance of magnetism.
The key.
Is what